Welcome to Weather Patterns 2.3. Today, in honor of May the 4th, is a very special Star Wars version of our science class. Today you will see the true power of weather. So, with that being said, remember how these videos work. You should shrink it, send it up to the corner, and leave it there, and have the video going while you are doing Amplify. So, make sure you've logged on to Amplify. This is Weather Patterns 2.3. For your warm-up today, you are going to look and put in order the events that happened in the Great Storm of 1862 in California. Now, in 2.2, you read about it, and so I want you to think back to what you read in 2.2 and put the events in order. Now, while you're doing that, let's listen to our science song.
The water cycle takes the water and moves it up and down and all around the earth. The water cycle takes the water and moves it up and down and all around the earth. The water cycle takes the water and moves it up and down and all around the earth. The water cycle takes the water and moves it up and down and all around the earth. Evaporation comes when the heat from the sun warms up all the groundwater, then it turns to water vapor. Condensation takes over, it goes up to the clouds. Water vapor cools down and it changes to a liquid now. Precipitation happens when the drops get big. It falls like rain, snow, sleet, and hail upon my head. I know it's the water cycle happening again. Evaporation, condensation, precipitation. The water cycle takes the water and moves it up and down and all around the earth. The water cycle takes the water and moves it up and down and all around the earth. Evaporation comes when the heat from the sun warms up all the groundwater, then it turns to water vapor. Condensation takes over, it goes up to the clouds. Water vapor cools down and it changes to a liquid now. Precipitation happens when the drops get big. It falls like rain, snow, sleet, and hail upon my head. I know it's the water cycle happening again. Evaporation, condensation, precipitation. The water cycle takes the water and moves it up and down and all around the earth. The water cycle takes the water and moves it up and down and all around the earth. Evaporation comes when the heat from the sun warms up all the groundwater, then it turns to water vapor. Condensation takes over, it goes up to the clouds. Water vapor cools down and it changes to a liquid now. Precipitation happens when the drops get big. It falls like rain, snow, sleet, and hail upon my head. I know it's the water cycle happening again. Evaporation, condensation, precipitation. The water cycle takes the water and moves it up and down and all around the earth. The water cycle takes the water and moves it up and down and all around the earth. The water cycle takes the water and moves it up and down and all around the earth. The water cycle takes the water and moves it up and down and all around the earth.
Well, now that we've had our distraction of the water cycle song, let's take a look at the answers to our warm-up. So if you look at what you had to select, our whole system starts by the sun transferring and warming up the Earth's surface. Remember that sunlight is absorbed by the Earth's surface and then is transferred as heat to the air parcel. Then that air parcel is going to absorb the heat and warm up, and it's going to rise up because warm air is less dense and so it floats. It's going to go up into the air part, go up into the surrounding air until it reaches the same temperature as the surrounding air. And doing that, it's going to transfer energy out along the way, and it's going to have water condense. That water condense is going to form water droplets, both as a cloud and rain. And so there's going to be a lot of rain. That rain falls and the form and will cause flooding. So when you look at your warm-up, that is our sequence. Today, we are going to continue our understanding and our investigation into what determines how much an air parcel will cool down. How do we know how much an air parcel will cool, how much energy will transfer out of it? And we've seen so far in both experiments, when we built our hot air balloon, as well as the article you read yesterday about the great arc storm that hit Southern California, in 1862. Today, we're going to continue on with that. So by the end of this lesson, our hope is that you understand what determines how much an air parcel will cool. So I want everyone to go to tab 2. In tab 2, you're going to reread our article, but this time, you're going to be looking for very specific clues. Today, I want you to go back through what you read on lesson 2.2, and I want you to figure out why does higher temperatures lead to more rainfall. So let me say that again. I want you to go to tab 2, and you're going to reread what we read yesterday. But this time, you are looking for very specific clues. You are trying to find why warmer air temperatures result in more rainfall. From our reading, you should see that there's a pattern that starts to develop. The pattern of warm air rising up, allowing more energy to transfer out to the air, which causes more condensation and more rainfall. Well, that term pattern is very important. In fact, that term pattern is a vocabulary word. So let's go ahead and open up our science journals and let's write down the word pattern. Pattern is something we observe to be similar over and over and over again. It's predictable. So our definition of pattern is something we observe to be similar over and over again. Now, with that being said, let's jump to the lab to see an experiment where we're going to be seeing how hot and cold mix together to make our storms.
Welcome to the experiment for this week. Since it is the week of May the 4th, Star Wars week, we are in our Star Wars costumes. Who are you today, Avery? Who are you today? What do you tell them over there? Are you Padme?
Queen Amidala.
Queen Amidala. So we have, and I'm Chewbacca. So, yep, we have the coronavirus, so we're doing experiments at home. So, I have a piece of equipment today called a convection tank. And this really long tank here is used for all sorts of experiments with convection.
Yeah,
and today,
even have old water and blue water.
we do, and we dyed it. And so this water over here we've set as cold water, and so it is actually sitting at about 15 degrees Celsius. And this is the orange side we put with hot water, and it's at 45 degrees Celsius.
Yeah.
Now, we're learning about weather patterns and how weather occurs. So instead of water, I want you to think about this as air. So when hot air and cold air are set up next to each other. So in a second here, I'm going to make this my hot air parcel. I am going to let that hot air parcel mix with my cold air. And what do you think is going to happen? What do you think, Avery, is going to happen?
Pulled up.
We're going to pull this one up. What do you think's happened when I pulled that up?
Water goes to the other side, then the other side.
You're right. Maybe they'll mix. Well, so we're going to try it in just a second. I have my assistant here. She's going to lift it up. Not yet. And we're going to watch it mix. But I want you to think about this, what you would see in the air. So you're going to kind of have to think that this is kind of tipped upwards. So while we're doing it, you're not going to get a really good view from this far off camera. So I have an iPad set up over here that's focused right here. Yeah, so you can see that actually happening really close up. So we're gonna see what happens when hot air mixes with cold air. All right, science dancer. So here's what I want you to do. I want you to go ahead and carefully lift that up. Ooh, let's watch it. And yeah, you can see mixing, but I want you to pay really close attention to the shapes that you see are happening here as this water mixes, because it's going to look a lot like clouds as that water causes turbulence and there's like formations that are occurring. In many ways, that's the same thing happens when an air parcel reaches up through that cold air around it. Hot air parcels lose energy to that surrounding air, just like the hot water over here lost energy to the cold side. And as a result, it's very turbulent, and you get lots of what we'd call gyres and different cloud formations, and which overall is going to cause condensation and rain as that energy is transferred to the cold surrounding air. So what you're seeing, even though it's water, is very similar than you're going to see in weather patterns.
What's the other appearance? And we make hot air balloon. I say when that was a quiet down, blah blah blah.
Yeah. Well, this is a lot like that experiment, because remember we had the hot air balloon that rose up. Well, this is the hot water, and we can imagine it rising to that. All right, what do you want to say to leave?
So we got this. We can dump water out for the little pups.
Yeah, we're not going to do that right now. But you're absolutely right.
Remember to subscribe to my dad's videos.
Back to the science lane.
Back to the science lane, everybody.
Now, while that's not exactly how weather works, it's pretty close, and we can use that to understand weather patterns. Well, let's try this now in a sim. So what I'd like you to do is go to tab 3, and we're going to jump into our sim. So in the article, you read about what caused the California rainfall, which led to that great flood of 1862, which we now call an arc storm. For example, we learned that when air parcels rise high in the troposphere, its temperature changes more as it loses more energy and it cools more, which causes more condensation and more rain. Today we're going to use the sim to kind of really get a better idea on how this all happens. And so you're going to jump into tab 3, and it's going to look just like this for you. So let's go ahead and launch our weather pattern sim as it comes up here. And for this sim, we are going to be using regional weather mode 1. So we're going to come over here to our menu. We're going to go to regional weather mode 1. And remember what you can change on this. You can change the amount of surface water, so the amount of water that's available for evaporation. You also can change the amount of sunlight hitting the surface. More sunlight hitting the surface means more energy is going to be absorbed by the surface and then transferred to the air parcel, or warming it up. If we have less sunlight, or no, we're going to get less energy absorbed by the surface and less energy pushed up into the air, or transferred up to the air. So for this one, we're really going to keep the surface water at level 5. So we're going to keep this throughout the sim. We are not going to change that. So if I wanted a severe rain, I would need a large amount of energy going to be transferred to that air parcel to make it condense. And for that, we could use like level 4 or 5. So let's go ahead and use level 4. And we're going to run and see how this all works. So if you notice, it's warming up. We started at 15 degrees Celsius. It's warming up, climbing up into the troposphere. As it goes up, we hit 6.5 kilometers. Now we are raining out down below. And there we have it. So let's go ahead and hit Analyze. There we go, Analyze. And we can get all the data that we need. And we're going to have a data table to kind of fill out down below. And we can see right here that we hit a rainfall level of 3. So not exactly as severe as possible, but still a pretty strong event. So let's go ahead and jump back and let's fill in all of this data that we just got. So we come back here and it says temperature, we're going to do test 1 together, and then on your own, you're going to do test 2 and 3, and then answer the questions down here below. But let's go ahead and take a look at this. So we had a severe rainfall event, and we need to see what is the temperature that air parcel stops at. So let's go look at this. And our final air temperature is right there. It is -30. So we come up here, temperature of the troposphere where the air parcel stops. Well, that is -30 degrees Celsius. Next, it wants us to find parcel height. And so if we come back up here, we can find parcel height. It is written right here at the very end, 6.5 kilometers. So that meant our air parcel climbed to 6.5 kilometers. And there's about 1.5 kilometers per mile. So you can kind of get an idea of what's happening there. It's about 4 or 5 miles up, about 20,000 feet. Air parcel, and that's estimating. The starting air parcel. So when we ran the sim, our starting air parcel started at 35 degrees Celsius. So we're going to write that, 35 degrees Celsius. And our final, well, we can look it up, or we can learn that, remember, it reaches the same temperature when it gets to the top, when it reaches equilibrium. So it's going to be -30 degrees Celsius. Oh, there we jumped in. Celsius. So let's check to make sure. Final temperature, -30 degrees Celsius. There it is. The difference in the air parcel temperature difference. There we go. Well, we can do the math, or we can look it up. And so doing the math, you have subtracting a negative means a positive, or we just write 65 degrees. And the amount of energy transferred out. Well, we saw that we lost, in this case, 168 megajoules. 168 megajoules. So we have seen and we explored how an air parcel climbing up into the air loses temperature. Well, you are now going to be jumping into this, and you're going to do test 2, test 3, where you're getting a little bit weaker of a storm, and a larger storm. Remember to keep this surface water at a 5. Don't change surface water, just change the sunlight to the surface. Once you've finished that, you need to answer these questions. What causes a parcel to stop rising? In which test did the air parcel rise to the highest? Is there a pattern between the starting air temperature and the parcel height? What pattern is there to the relationship between parcel height, rainfall level, and why? So you need to answer these 3 questions. Go ahead, and when you're done with that, hit that hand in button.
Now, from our sim and the experiment, as well as what we read, we should be able to put this all together in some key concepts. So let's go back to our science journal. And our first one is we're going to go back to key concept number 3. Now, before, key concept number 3 said, energy transfers from warm air to cold air until the temperature becomes equal. And remember, we talked about equilibrium. Well, when we're talking about weather, we can add something to this. So, what I'd like you to do is to revise key concept 3 to add, as an air parcel rises, energy transfers from warm air to cold air until the temperatures are equal. So we are going to add that very first section that really, when it comes to air, it's as an air parcel rises, that energy is going to be transferred. So, like we have, a hot air parcel rising up into the troposphere, transferring energy to the surrounding air. And I also want us to add now key concept 7. Now that we can put all of this together, we can see that when an air parcel is warmer, it rises higher and its temperature changes more as it loses energy.
this would cause more condensation and rain. So we could put it, this is putting it all together that we've learned. So our key concept 7 says, when an air parcel is warmer, it rises higher and its temperature changes more as it loses energy. This would cause more condensation and more rain. So when an air parcel is warmer, it rises higher up in the troposphere and it's going to lose more energy in doing so. So more condensation. So key concept 7 really is the answer to our investigation question. The past week, we've been exploring what determines how much an air parcel will cool. And when we put it all together, we can see that it's in key concept 7. That when an air parcel rises up, the higher it goes, the more energy it transfers. And we've also seen that warm air parcels will rise higher into the troposphere, losing more energy. So, what determines how much an air parcel will cool? Well, how hot it is to start means it'll rise up higher, and how high it goes in the troposphere determines how much energy it will transfer, and cause condensation, and eventually precipitation. So, to show what you have learned, we want you to go to tab 4. Tab 4 is going to be your homework tab. So when this video is done, go ahead and log on to tab 4. But I do want to spend just a second to remind you how these videos work. You can always go back, re-watch the video. You can hit pause or go back and watch a section that you really want. But always remember to keep moving forward.